So thank you very much for the kind invitation to participate in this workshop about generalized complex geometry. As I mentioned in my talk, in my title, unfortunately, I have very little to contribute to the theory of generalized complex structures, even though I hopefully have something to say about generalized geometry. So today I would like to start talking about generalized scalar structures, which do include generalized complex structures as part of the structure, and the relation to physics. And somehow the main motivation of my talk, or like the main goal, is try to draw a path towards trying to do some rigorous mathematical constructions which go by the hand of physics, which is, I guess, the origins of many developments in generalized geometry. And the first thing we will see is that if we want to literally follow what physics says, then we will find some obstructions and some no-go theorems that make our setup to be kind of trivial. I mean, at least go back to Kähler manifolds and algebraic manifolds and so on. So in order to be able to do these mathematical constructions, but like trying to mimic what physicists expect us from general geometry, I will have to weaken some of the conditions, and this is how we will go to this territory of natural structures in general geometry, which do not include generalized complex structures. They include some sort of two halves of generalized complex structures, but they are not one generalized complex structures per se. So okay, so let me start. So generalized scalar geometry starts trying to understand the geometry of a nonlinear sigma model in physics. This is a physical theory where the fields are maps into some surface, which possibly with boundary you can think of this as a cylinder, into some target manifold M. And this geometry, this generalized scalar geometry, arises when we impose that this field theory is supersymmetric, suitable symmetry between fields, bosons, and fermions in the theory. Anyway, so if let's see how this manifests in terms of the geometry. So suppose that we are in the context of type 2 string theory, then our manifold is going to be 10-dimensional, and it's going to be endowed with a Lorentz metric, which I'm going to denote by G10. And this 2,2 supersymmetry imposes the following answer. So we have some Lorentz metric G10, some 3-form H10 in this 10-dimensional manifold, and we have a pair of spinors with the same chirality. So this manifold is a spin, satisfying these equations here. Oops, something is going wrong. Anyway, so this is just the Levi-Civita connection acting on the spinor. This is the multiplication of the 3-form acting on the spinor thought of as a 1-form with values in lambda 2, which is the same as SO. This is acting on the pair of spinors, so you have to think of this acting on every element in the pair. And then this RR stand for corrections to these equations. We have to do with other fields in the theory, which are called Ramon fields. And in type 2 string theory, these are going to be odd-dimensional or odd-degree forms. So essentially, up to the Ramon fields, this is telling us that the two spinors are parallel with respect to the connection, the metric connection with total skew symmetric torsion H10. Okay, one with respect to H10 and the other with respect to minus H10. Okay, and then we have this other equation, which is called usually this is called the Gravitino equation, the first one, and the second one is usually called the Di Latino equation, and it tells you that the Dirac of Levi-Civita plus Now the three form acting by Clifford multiplication in all indices on the pair of spinors is 1/2 of d of a function. This function phi 10 is on the 10-dimensional manifold, is called the dilaton, acting on the spinor, plus this Ramon thing. Okay, so in my talk, I'm going to set mostly all the Ramon fields to 0, but it's interesting to consider these more general geometries in some cases. Okay, so a 2,2 nonlinear sigma model requires the existence of this pair of spinors satisfying these equations. For a suitable background Lorentz metric G10, a suitable three-form H10, and a suitable function phi10, which is the dilaton. Now, if we assume the standard or the usual compactification ansatz to make link with Riemannian geometry, then we have that our 10-dimensional manifold is some Lorentz 10 minus k dimensional manifold cross some k dimensional manifold M. And then a suitable ansatz for the spinors. The spinors above were in 10 dimensions. So I have to construct spinors in 10 dimensions from spinors in k dimensions. This can be done. There is some formulas, but suitable embedding of this pair of spinors in k dimensions in 10 dimensions produces from these 10-dimensional equations the following system of equations. I didn't say, but the three-form H10 needs to be declosed. And here I have now a three-form H on the k-dimensional manifold, which is declosed, a Riemannian metric G. G is now Riemannian on MK. Phi is now a function on MK, a smooth function on MK. And then I have a pair of spinors, eta plus and eta minus, which I'm going to assume to be pure, because it is a case interesting for the physics, I guess. And satisfying the following constraints.
Sorry, Mario. There was
Yes.
a question in the chat.
Oh, yeah.
What about the meaning, the physical meaning of the two equations that you wrote at the very beginning? Yeah.
These two equations?
Mm-hmm.
Yeah. So the meaning is, the physical meaning is you have a field theory where the fields are these maps from sigma 2 into M, okay? And you have a Lagrangian. You have an action, functional, whose critical points are the classical solutions of your field theory. And if there was nothing, if M were like flat n-dimensional space, this equation will tell you with the Lorentz metric, this equation will be just the wave equation for sigma, okay? But because we have these background fields, then there is some complicated sort of harmonic equation with respect to Lorentz metric, etc. Okay, and now you have the space of solutions of the classical field equations, and you want this space of solutions to have symmetries in a suitable sense. So you want this space of solutions to have at least asymmetries by the action of a Lie algebra, which is going to be actually a super Lie algebra. And the meaning of the killing spinor equations, of these equations here, is precisely that there is a suitable Lie algebra which acts on the space of fields, which satisfy the classical equations. Okay. It's even more than that. This constraint of having the two spinors satisfying the equation is going to tell you that the Lagrangian, the functional, is invariant under the action of this Lie algebra. Is it clear?
For me, yes. Thanks.
Are there more questions?
What are the pure spinors?
Sorry?
What are the pure spinors?
Oh, so the pure spinors eta plus and eta minus are going to give you. So you are going to construct a specific solutions of these 10-dimensional equations from an ansatz, which is as a manifold is a product. The metric is going to be also a product, maybe a word product. And the spinors in 10 dimensions are constructed out of these two pure spinors in k dimensions and one Lorentzian spinor in 10 minus k dimensions.
I meant, what does pure mean?
Pure means that in the case where I'm interested in, which is the case that k is even, is going to mean that the Clifford multiplication by elements in the tangent bundle give you a subspace which is half-dimensional in the complexified tangent bundle and gives you an almost complete structure.
Okay, thank you.
Okay, so pure means that when you act with the tangent of the manifold MK, complexify, the annihilator of the spinor is precisely half-dimensional. Okay?
Okay,
And
thank you.
actually defines an almost complete structure on your manifold. Okay, good. Something erased my equations. I don't know what happened. Anyway, let me do it again. I'm going to stop sharing and share again because the equations disappeared. I don't know why. Okay, screens. No, let me do it again. Share here. Okay, good. Back again. Okay, so I have my equations now in k dimensions, which are these two. Formally are the same. I have chosen an ansatz, a product ansatz, so that the equations in k dimensions formally look like the same as in 10 dimensions. Now I have written this not in terms of a pair epsilon epsilon 1, but actually in terms of the two spinors eta plus and eta minus. So what I have is that the three form is closed, and then eta plus is parallel with respect to the connection with a skew symmetric torsion H. Eta minus is parallel with respect to the connection with a skew symmetric torsion minus H, metric connection. And then I have these other equations which are given by Dirac with respect to the connection with torsion 1/3H and the connection with torsion minus 1/3H. And then this correction coming from the dilaton acting on the spinor. So the first, these equations which make parallel spinors are called usually gravitino, and the second equations are usually called dilatino. And now this is the link with almost complex structures, or if one with complex geometry, which I guess is the main topic of this meeting. So Gates, Hall, and Roschek in '84, and also Strominger and Hall for this specific ansatz for the spinors that I'm writing down, show that if your manifold is 2n-dimensional, then the thing I was explaining before applies, so that a pure spinor determines an almost complex structure on your manifold, given by the annihilator of the spinor in the complexified tangent bundle. Then these killing spinor equations plus and minus are equivalent to that the two complex structures determined by eta plus and eta minus are integrable, actually that they have holomorphic volume forms, that the three form H is written down in terms of dc of the two Hermitian structures. So omega plus is the contraction of the metric with J plus, omega minus is the contraction of the metric with J minus. So there is this agreement between H and minus plus dc of the two omegas with respect to the different complex structures. And actually the differential of the function is actually plus minus 2 times the Lie form with respect to the complex structures. And recall that the Lie form is the rotation with respect to J, and in this case, for example, J theta omega plus is going to be rotation with respect to J plus of V star of omega plus. Okay, so in particular, I mean, there are many experts in the audience, but in particular, this thing here is telling you that they have the so-called B-Hermitian data, which is equivalent to a generalized Kähler structure. Okay. Okay, so far so good. So we have these equations, and now there is a theorem of Maldacena-Nuñez which tells you that actually, if we assume that our manifold is compact, and I guess this is for me one of the main, I mean, you really want this for some constructions, then the only solutions to these Bianchi identity equations, so the dh equals to 0, and the Killing-Spinor equations have h equals to 0 and d phi equals to 0. So in particular, h equals to 0 implies that the two complex structures are Kähler. Okay, the two omegas are Kähler. So
Can I ask you something?
Sure.
When you write in KS plus and minus the fact that these spinors are parallel, does it imply some reduction of the holonomy in this case?
Oh, sure. Yeah, this implies that the holonomy reduces to SUN. Yeah.
Okay, thanks.
Yes. Yeah. Okay. So we have the physical equations, and they are nice and beautiful, but there is nothing on compact manifolds beyond Kähler. This will actually imply Kähler and Ricci flat, because the holonomy of bismuth will reduce to SUN because of this equation here. And because it's Kähler, bismuth is the same as Chern, which is the same as Levi beta. So Levi beta will be actually Ricci flat. Okay, so let me recap the proof because I think it's illustrative. And actually, it tells you that it's not so easy to relax these equations, because actually it's not that if you have two spinors, the equations imply Kähler. It's sufficient to have just one solution to the Killing-Spinor equations. I mean, just one eta plus or eta minus. So assume that I have Bianchi identity and the Killing-Spinor equations in the plus, nothing more than that, okay? Then I have two conditions. One is that the bismuth-Ricci, I mean, the Ricci for the Nabla-Plus connection is 0, and these are these two equations, A and B. And there is a more intricate equation. It's a sort of Lignerovic type formula, which tells you that on top of these two equations, which physicists will tell you are like the equation of motion for the metric and the equation of motion for the B field, there is an equation of motion for the dilaton, which is this scalar quantity. So here Ricci G is the Ricci tensor. This is the unique symmetric tensor that you can cook out of a free form by contracting one index of each, two copies of the free form. This is just the usual thing, like gradient, Lie derivative of G. This is the Hodge star, the dual of the Hodge star. Sorry, the Hodge dual of the exterior differential acting on H. So this is a 2 form. This is the 3 form contracted with the gradient, and this is more self-explicative. This is the scalar curvature. This is norm squared in Hodge norm of the 3 form. This is the Laplacian d star d, and this is the norm of the phi squared. Okay, so what do you do now? You trace A and subtract C, and then you get this equation here, minus h squared plus 2 d star d phi plus 2 norm d phi squared equals to 0. And now you realize that actually this quantity here is up to the exponential of phi is a Laplacian. So now you do the following: you multiply by e to the minus phi times the volume, integrate over the manifold, the Laplacian goes away because the integral of the Laplacian is 0, and then you get that the L2 norm of H with respect to this volume is 0. Therefore, H is 0, and now you go back to this equation and integrate again, but this is already a Laplacian. So this will tell you that d phi is also 0. Okay? So if I have a solution just of one Killing-Spinor equation, not two, just one Killing-Spinor equation, then I have that the H is 0 and the d phi is 0. And let me ask something to the audience. Where did I use that H is D closed? Sorry, I know it is politically incorrect to ask questions to the audience, but where did I use that H is D closed for this proof? I have used it, but where? Any guess? Well, I have used it for deriving this equation here. Equation C is a linear type formula which means that it's a difference between the square of a Dirac operator for the 1/3 connection, like the one which appears here upstairs. This one here, squared, minus the rough Laplacian acting on the spinor. It gives you precisely this quantity only if dh is 0. Otherwise, you get dh acting on the spinor. Okay? So it is key that I have the Bianchi identity as well. Okay? Any questions so far? You are not doing the exercises. I'm a bit annoyed. Anyway, so let me continue. So what is the relation to generalized geometry? Well, there is a standard construction in geometry, which is that if I have two copies of the spinor bundle of a manifold and I tensor them, I get polyforms. So this way, physicists, in particular, I didn't write the reference, but this is by work by Waldron, Minasian, Petrini, and Tomasiello. They show that instead of considering this pair of spinors, you can consider corresponding polyforms, A and B, which are cooked up out of eta plus and eta minus. And of course, if you know about generalized geometry, polyforms can be thought of as spinors, but now not for the metric, but for the neutral pairing on T plus T star. Okay? You hear me, right? Can anyone say that you hear me, please?
Yeah.
I can
Yes,
hear you
I-
at all, actually.
Sorry?
It's okay.
Okay, good, thank you. So the point is, out of this pair of spinors, you get this pair of polyforms, phi I and phi B, which are regarded as spinors for the neutral metric on T plus T star, the usual current algebroid, and the standard current algebroid. And on this current algebroid, I do not put the untwisted bracket, but actually I put the twisted Dorfman bracket by the tree form H. And if I do so, then the Killing spinor equations give you solutions to the following. So they give you that these phi AB are annihilated by DH. DH is you take the exterior differential acting on polyforms, and then you add a term which is H wedge the polyform. Okay, and this is not this is preserving the set 2 grading, but not the set grading. It's the usual twisted differential in general geometry, or if you want, is the Dirac generating operator in T plus T star, if you like that thing. Okay, so this is one of the two conditions that the Killing spinor equations give you. This is what these physicists that I mentioned discovered. But also, there is this natural quantity, which is on polyforms, there is a natural pairing called the Mukai pairing. And this gives you a volume form. And you take the ratio of this volume form corresponding to phi A by this other volume form corresponding to phi B. This is a function. And it turns out that this function is actually constant. So the Killing spinor equations imply that this ratio of volumes is constant. And this is sometimes called the generalized Calabi-Yau equation. We can be a bit more explicit about how is like the dictionary between these two points of view, thanks to a nice result by Apostolov, Fu, Stritz, and Justinowski from 2022. All these formulas are very obscure in the literature until this paper appeared. Now, for me, this is very clarifying. So for any generalized Kähler structure with holomorphically trivial canonical bundles, and this means that you have the two generalized complex structures are given by are are given by complex pure spinors, which are the H closed. So if we impose a star, then the following holds. So firstly, let me go to the right-hand side. This function is actually the potential for the Bismuth-Ricci form of the two complex structures with respect to their corresponding complex structures. So that means that the Bismuth-Ricci form of omega plus, for example, is minus a half dj plus of d phi. So it's like this is TDC of the function phi. Okay. So in particular, because this is constant, this is 0. Okay, this is in my physical setup, not in this proposition, but in the physical setup where I impose the Killing spinor equations, this is 0. I'm not imposing now compact or anything. It's on any manifold. If I understood correctly this proposition in this paper. And the second thing relates the Tully forms. And recall the Tully forms. The difference of the Tully forms in our setup is precisely the differential of the dilaton, not the dual. So the difference of the Tully forms is actually the Poisson tensor corresponding to the Hermitian data acting on d of the function phi, which is this difference of log of the difference of the ratio of the two volumes. And this sigma is a natural tensor discovered by Hitching, which is essentially the commutator of the two complex structures. Okay, so here we see very clearly that if we have the physical equations, then we'll have the Bismuth-Ricci 0 is even more than that, that the two Lie forms differ precisely by sigma of the d of the dilaton. Or you want sigma of the ratio of these two functions. Yeah, I said it wrong. So this is the two Lie forms differ by sigma of d of this ratio, but actually the two Lie forms are actually the difference is the gradient of the dilaton. Okay. So there is this interesting relation between the Bismuth-Ricci potential and the dilaton function in the physics. Okay, and now let me go to the thing which is probably very familiar to many of you, which is how do you write down this big Hermitian data? So the two complex structures with a metric, both complex structures are orthogonal. The torsions DC omega plus, DC plus omega plus, and DC minus omega plus minus are opposite and D-closed. Well, Gualtieri in 2004 in his PhD thesis proved this very illuminating result, which actually led to many developments in the area of generalized geometry, which is that big Hermitian data can be recasted as two generalized complex structures. So you take E, you complexify E tensor C, and then J, you don't need to do that. You take E as a real bundle, which is T plus T star, and then JA and JB are going to be orthogonal transformations with respect to the natural pairing. It's a squared, is going to be minus the identity. They are going to commute, and they are going to give you a positive metric on E when combined in this way with the neutral pairing. Okay, so this is how these physical equations led to the discovery of generalized Kähler structures and generalized complex structures, etc. Of course, for having a generalized Kähler structure or even a generalized complex structure, you do not need to impose the full equations. Okay, so you just need the big Hermitian data. You just need the metric, the closed free form, the two integrable complex structures, such that the two torsions are related by one is h and the other one is minus h. Okay, but you don't need to impose the other equation. So it means that there are compact examples, or there are plenty of compact examples. But if we want to make the link with the physics, so if we want to solve the physical equations, then the only solutions are Kähler. So then I go to the following question, which is the main point of my talk, I guess. Let me make it bigger. This thing here. So how can we weaken this killing spinor equations plus the Bianchi identity in such a way that on the one hand we avoid this Maldacena-Nuñez no-go theorem on compact manifolds, and on the other hand we preserve qualitative features of this physical theory, the nonlinear sigma model, in such a way that we can talk about things like mirror symmetry or, for instance, holography on these manifolds. Okay? This is my goal. Of course, there are many ways of weakening this, of making this weaker. One is just forget about any equations and just think of generalized complex structures or generalized Kähler structures. But I really want to make the link with the physical theory. And for that, for at least for some features of that, I really need to think, I really need to keep the information of the metric, satisfying some PDE, which is meaningful. Okay, so notice one thing. So the two generalized complex structures, sorry, this should be a square here. J squared AB is minus identity, which commute induce a fourfold decomposition of the complexification of the current algebroid, where LA and LB are given by the I eigenspaces for JA and JB respectively. Okay? So there is this fourfold decomposition. This was discovered by Marco Gualtieri, and it leads to very nice relation to holomorphic Dirac geometry, etc. And in a minute, this is going to appear in my talk again. So how can we relax this theory in a physically, not physically consistent, but at least physically meaningful way, or at least some of the, like we can proceed mathematically trying to parallel the physical theory and to construct, invariants, partition functions, things like this. So one way is to relax the Bianchi identity. So instead of imposing that dh is 0, which you want is the birth of generalized geometry, this is how we work. We start with a closed free form, and then we have a current algebroid. Instead, we have a source, delta. And in some cases, we know how to tackle this, because, for example, if the delta is some Pontryagin term, like trace f squared, where f is the curvature of a connection on a bundle, then this leads to other classes of current algebroids, string algebroids, and the baby case of this, which is BN generalized geometry that Roberto will talk about tomorrow. Also, other cases where you have Leibniz algebroids, more general, and this makes the link with exceptional generalized geometry, like the study by Waldron, Charlie Strickland-Constable, Coimbra, and many other people, Ashmore, Tennyson, etc. Another way to turning on these deltas is to turn on some Ramon fields. They appear in the type 2B equations naturally. Okay, this case is at least the case with gauge fields we understand. We can proceed. There is a generalized geometry that we can do with this. Or also the case with Leibniz algebroids. In some cases, we can proceed and do some generalized geometry with that. But I think that one of the most interesting perspectives of this field, generalized geometry, is to be able to understand the case with singular sources. I think this is, the day we understand how to construct algebroids, where you have singular sources, meaning that delta is a distribution supported in some submanifold, and that day we will be able to say many interesting things about the topology of the manifolds with this type of geometries. Okay, so this is one possibility, to relax the Bianchi identity. Another possibility, also related to this Ramon, is to relax the killing spinor equation. Say, not assume the full holonomy to reduce, maybe only the local holonomy, something like that. And this can be done by imposing these Ramon fields, for instance. Another possibility is to drop one of the killing spinors, for example, not consider eta minus. But we have seen that this is still a problem. So this cannot be done on its own, because in my proof of the Maldacena no-go, I only use one killing spinor. I don't need the two. Okay, so this is not enough, certainly. I need to combine C. If I want to do C, which I will, I'm going to combine it with either A, B, or D. And the other thing that one can do, that we use in the proof of the Maldacena no-go, we strongly use the fact that d phi is d of a function. I mean, the function is global. So is to promote d of phi to be an arbitrary one form on the manifold. And somehow this is natural, because we have seen in the previous proposition by Apostolov and Streets, Fu and Justinovsky, that, for example, d of phi is just the difference of the Lie forms, essentially. So why not to let it be an arbitrary one form, maybe a one form with suitable properties, nice property related to the metric or something like this, like maybe like a killing field, okay? Okay, so let me now go to any questions so far? Okay, so let me go now to the geometry I'm interested in, which is this 0,2 geometry. And this is what I advertised in my abstract. It's a very weird geometry, because we take a half of a generalized complex structure and another half of another generalized complex structure, and they combine, but they do not give you one generalized complex structure. Okay, so it's a kind of a weird condition. So I'm going to take a current algebroid, which for a minute is going to be transitive, but most of the time is going to be exact, t plus the star. And my 0,2 geometry is going to be given by a subbundle of E tensor C, satisfying the following constraints. So the projection of L plus L bar is the complexified tangent bundle. So it is actually transitive over L plus L bar. Actually, it is an isomorphism. Okay, I didn't write it down, but it's an isomorphism on T plus on L plus L bar to Tm tensor C. L and therefore L bar are going to be involutive. Okay, I didn't write it down, but I should have. L is isotropic. Okay, otherwise this is wrong. L is isotropic as well. And furthermore, and also L bar are both isotropic. And furthermore, when I do the pairing of something in L with its conjugate, is going to be positive unless the element is non-zero. So here I'm thinking of this L plus L bar in E tensor C as a half plus a half GCS because of this nice decomposition by Gualtieri. So if you have a generalized scalar structure, so we have two generalized complex structures, then one is given by L plus L minus, and the other one is given by L plus L minus bar. Okay, so here I'm essentially dropping this part, just considering this structure here. So I have a half plus a half, but this is not a GCS. Okay. So what does L gives you? Well, L essentially gives you a priori closed metric. This is the idea. So on the one hand, if I take the real points of L plus L bar by conjugation on E tensor C, I get a generalized metric. A subbundle says that when I restrict the pairing, it's positive definite and it's isomorphic to the tangent bundle via the anchor map. I also get, because pi projects isomorphically into the complexification of the tangent bundle, I get a decomposition of Tm tensor C into two complementary subspaces. But this is precisely an integrable, an almost complex structure on M2. And now the involutivity condition is going to tell me that this integrable, this complex structure, this almost complex structure is actually integrable from the fact that the anchor is bracket preserving. And I get something else which is very interesting and which is actually related to the dilaton. I have if I take holomorphic coordinates in my manifold with respect to this integral complex structure, I have a family for each holomorphic open patch. I have a family of sections of the kernel of the anchor map, which are given by the unique solutions to these equations, where the sub L is the projection into L, and these things are frames of L bar and L, which are mutually dual and satisfy some other constraints which I'm not going to tell you. Okay, but not only I have a generalized metric and an integral complex structure, but actually have this local section. So for example, let me show you in one case I like. So if I have a transitive current algebroid of the form T plus the adjoint of a principal bundle plus T star, so if you don't like principal bundles, remove this part, then the Bianchi identity is enhanced to give you dH equals this Pontryagin term, this like trace F squared. Fa is the curvature of a connection on the principal bundle. The involutivity of L does not only tell you that the complex structure J on the tangent bundle is integral, but it also tells you that the three form H satisfying this Bianchi identity is minus dc of omega, where omega is again the rotation of the metric with respect to the complex structure J. And in this situation, this epsilon L is very explicit. Is this combination of a complex one form that some of you may recognize. Omega is a local holomorphic volume form. So this is a local trivialization of the holomorphic canonical bundle. And some of you may recognize that this is just the one form connection in this trivialization of the induced connection on the canonical by the bismuth connection. So this is like the bismuth one form on the canonical. It's like the bismuth connection, essentially, in this trivialization. And these other terms is like the trace of the curvature with respect to the deformation metric. And now the type of geometries I'm going to be interested in are, I'm going to call them canonical, why not? So L plus L bar satisfying all these constraints is canonical if when I consider the insertion of this section of the kernel of the anchor map into the bracket, this is 0. And you say, okay, but epsilon L is just a bunch of one forms which depend on the coordinates. But actually, this quantity does not. This is always well defined. And what is this? You think of this formula. So essentially, if I insert a one form in the bracket, forget about the complicated bracket coming from T plus T plus T star. Just think of the usual Dorman bracket on T plus T star. If I insert a one form on the bracket in the first position, it just gives me D of the one form. It's like the B field transformation, the infinitesimal B field transformation given by D of the one form. And D of this one form is globally defined, is the Bismuth-Ricci form. Okay. So my geometries, my canonical geometries in particular, are going to be Bismuth-Ricci equals to 0. And because H is minus dc omega, if I have no bundle, they are going to be actually given by pluriclosed metrics with vanishing Bismuth-Ricci form, which some people like me call Bismuth-Hermite-Einstein. So this is a comment that this is always giving you a well-defined element on the Lie algebra of the automorphisms of E tensors. So one nice thing is that why canonical, what that has to do with the theory of canonical metrics in ordinary complex geometry. Well, if L plus L bar is canonical, you can construct a holomorphic current algebroid, which is given by, a current algebroid in the holomorphic category, which is given by taking the perpendicular to L bar quotient by L bar. This is actually isomorphic to B minus tensor C. And therefore it has a natural Hermitian metric given by the ambient metric restricted to B minus and conjugating the second. And I put a minus because this is naturally negative definite. So I want to make this as positive as possible. And then this being canonical implies not only that this is a holomorphic vector bundle, but also actually that this metric with respect to this holomorphic structure is Hermite-Einstein. So satisfies these natural equations that people have studied ever since the 80s in geometry in relation to the Donaldson-Uhlenbeck-Yau theorem and the Hitchin-Kobayashi correspondence, etc., etc., etc. Okay? So my canonical geometries actually give canonical geometries on holomorphic Courant algebroids in a more standard sense. Okay, so let me go to this example. So as I said, if I take E to be T plus T star, this leads to Bismuth-Hamilton metrics. These are equivalent. These conditions of being canonical is the same as a pluriclosed metric on a complex manifold.
Mario, there
Yes.
is a question in the chat.
Sure. Which says what? Let me see if I can see.
It's asking what is L in the example.
What is L? What do you mean? L? This?
I don't know what it means.
I don't understand what it. Let me see if I can. What is the chat?
Is it possible that's this holomorphic Courant algebroid? The T10 type of thing?
Yeah. Can you say it again, Jill? I didn't.
Yeah, I was like the only L that I see is this L plus L bar that you're writing all over the place. That is the T plus T star but holomorphic. Maybe that's the. Does that
Yeah,
answer the
there is a canonical construction by Marco Gualtieri, which says that if you have a lifting of the tangent 0, 1 with respect to a complex structure, which is this L bar, then if I take the perpendicular to this and I equation by L bar, it gives me a Courant algebroid in the holomorphic category, which is non-canonically isomorphic to T10 plus T star 10. Yes. Does this answer your question?
I guess like a explicit example would be when L is T10 for it. Is that right? If you have a complex manifold, you can take L to be T10 sits inside T plus T star.
Your Q would be T10 plus T star 10.
Yeah, but the L alone would be just
The
T10, right?
L bar will be T01.
Yeah, okay.
Or if you have a metric, little omega is going to be e to the I omega acting on T01 inside the complexification of T plus T star.
I guess. Does that answer the question? It wasn't my question.
Okay.
It was from the bit.
Okay. So anyway, so this Q is isomorphic to B minus tensor C. This has a metric, and canonical means these equations are satisfied. So there are two interesting cases at least. One is the standard case, T plus T star. This leads to Bismuth-Hamilton symmetry, so metrics which are pretty closed, SKT, and have vanishing Bismuth-Ricci. And the other one is this case that I'm been studying for a while, T plus T plus T star, where you have a weak version of the Hall-Strominger equations, where you have vanishing Bismuth-Ricci, or not quite, because there is a correction coming from lambda f, and you have that the connection on the bundle is Hermite-Nuñez. Anyway, particular cases are solutions of the Hall-Strominger equations. Okay, so the interesting thing about this, or the thing I like about this, there are many compact examples with H non-zero. The first case are just even-dimensional compact Lie groups. So G is compact, even-dimensional. Okay, the complex structure is going to be left invariant, and the metric is going to be bi-invariant. This has been known for a long time, ever since nice papers by Gil and Marco Gualtieri. Actually, these examples are generalized Kähler because you can extend on the left and on the right the complex structure on the Lie algebra. And they are Bismuth flat with respect to the two connections plus and minus. So they are automatically Bismuth-Ricci flat. And then there was for a while this question about whether one could construct solutions of the Bismuth-Hamilton equations on compact manifolds which are not Bismuth flat. And then, well, therefore, first there was some interesting development by by Beatrice, Brienza, Anafino, and Georg Grancharov, who showed that you can actually construct examples by taking local products of bismuth-flat and Kähler. And then there is more recent construction, which is, to my taste, is very interesting, more interesting, which is constructing examples which are not locally products of Kähler by bismuth-flat, which is on manifolds of the form S3 cross S3 or S1 cross S2 cross S3. And I'm not talking more about this because Besti is going to tell you all about this in his talk. What I want to tell you about is this theorem with my collaborator Lorenzo Foscolo, which tells that considering these geometries, these canonical 0-2 geometries, you actually do have a path towards understanding generalized geometry with distributional sources. So with Lorenzo, we studied complete non-compact examples of the Bismuth-Hamilton equations, which actually have a well-defined dilaton. So these are solutions of the so-called type 2b system. On the cotangent of the 3-sphere, our examples are complete, have the metric is complete, and it's actually asymptotically conical, Calabi-Yau. The metric at infinity is Kähler. And they have a well-defined dilaton, they have H non-zero. And actually H is very neatly tied to the geometry. We did this by means of reducing to an ODE, so by imposing homogeneity 1 and such. Okay, this is great. We have some complete non-compact examples, which I think are essentially the first of this sort. But actually, we show that if instead of considering T star of S3, you consider the small resolution of the nodal point singularity, which is the total space of O minus 1 plus O minus 1 over CP1. This is a Calabi-Yau threefold non-compact. Or if you consider the total space of the canonical over CP1 cross CP1, then the only solutions of these equations with well-defined dilaton and have this HU2 cross HU2 symmetry, so they are homogeneity 1 solutions, are actually singular and solve this distributional Bianchi identity. So this means that the three form, the C omega is locally L1, and its distributional D is a current of integration along a submanifold, which is actually codimension 4 real or codimension 2 complex, and it's actually located as a holomorphic curve, which in this case, for example, is the zero section of the bundle over CP1. Okay, so it is very interesting that just by considering the equations without trying to find any of the singular sources in the Bianchi identity, we have actually just the equations tell you that these things are there. You cannot avoid them. Okay. Okay, so do I have 5 more minutes, or I don't know? I think I started late, but I was going to say something about holography.
Yeah.
Sorry?
Yeah, you can have for 5 minutes, I guess.
Okay, so I promised that I wanted to say something about how generalizing or extending in a suitable way the physical equations may lead us to understanding mathematically some aspects of these physical theories. And lately I've been interested in a particular setup which is related to holography. And it's related to a paper by Witten, which several people like Beatrice and collaborators have been studying, which is this paper by Witten called Instantons and the Large N=4 Algebra. So holography is a duality, it's a quantum duality in string theory, or it's not even a string theory. The duality is something more general. Anyway, so duality is a duality in physics which relates a supergravity theory or a gravity theory with some conformal field theory. And the point is that the supergravity theory lives in some, in this case, 10-dimensional space, but this has a well-defined conformal boundary, and the conformal field theory lives in the boundary of this space. So the case that Witten is interested in particular is the case of ADS3, cross S3, cross S3, cross S1. And what Witten proposes in this paper is that the two-dimensional sigma model, sorry, the conformal field theory dual to this supergravity background. So I consider a suitable Lorentz metric in this manifold, which is Lorentz in ADS3 and is Riemannian in here. He argues that the conformal field theory dual to this is a two-dimensional sigma model with target the modular space of anti-self dual connections on a Hopf surface or quotients, finite quotients thereof, so like primary or secondary Hopf. And the main thing that he explores in his paper, and also in papers by Papadopoulos, joint and independent, is the fact that for many, many years, physicists have known that the supergravity theory corresponding to this geometry, ADS3 cross S3 cross S3 cross 1, has a particular symmetry. And this is called the large n equals 4 algebra. And the whole point of Witten's paper is to show, to give evidence, and also the papers by Papadopoulos, to give evidence that this large n equals 4 algebra also appears naturally in this modular space. Okay, so they do it by their physical means, which I do not fully understand. And the thing we have been trying to understand more rigorously lately is how to realize this proposal using some machinery called the chiral-Lebrun complex. Okay, so for this I need to tell you something about the n equals 4 algebra. So we can think of this is really a vertex algebra, but we can think of this large n equals 4 as an infinite dimensional Lie superalgebra. The generators are this Ln, Jnk, Gm, and then this other thing which I call X and X tilde. So Ln is actually generating, there is a set worth of these L's, and these generate the Virasoro vertex algebra, the Virasoro Lie algebra. These are even elements. Jointly, the Ln's, which are indexed by the integers, or sorry, Nm should be in Z, not in N. Okay. So these Ln's, which generate Virasoro, jointly with the Gm's, which are indexed by half integers, generate an extension of Virasoro called n equals 1, or Noves bars. And then there are 3 copies of these Jnk's, which generate some other extension of n equals 1, which is called n equals 2. So in the small n equals 4 algebra, we have these generators, which are giving you extensions of the Virasoro algebra. In the large n equals 4 algebra, there are more generators. There are also 2 families of generators, also indexed by 1, 2, 3, and which are satisfying suitable relations, whatever. So Witten argues that the corresponding conformal field theory also does have this n equals 4, large n equals 4 symmetry. So how can we understand this rigorously? Well, the proposal here is the following. So this is part of Witten's argument, but I'm going to tell you a bit more, hopefully. So you take S3 cross S1. This has a triple of 0-2 structures satisfying the quaternionic relations. This is also called a strongest case D. Okay, so there is one torsion, H, one metric, but there are 3 coprostructures satisfying the quaternionic relations, and all of them are pretty closed. So I have the same as before, these 0-2 geometries, but coming in a triple, and the J satisfy the quaternionic relations. And then there is a theorem by Moraro and Verbitsky, which tells you that if you have a manifold which is a strong HKT, then the moduli space of anti-set dual connections is also a strong HKT. Okay, this is what Witten and Papadopoulos are using for claiming that there is this also large n equals 4 algebra in the CFT. So let me try to make this a bit more precise. So the conjecture that I want to present here is that any strong HKT structure induces a well-defined, totally rigorous, mathematically fine representation of the large n equals 4 algebra on some crazy vector space, which are the global sections of something called the chiral rank complex associated to the current algebroid E tensor C. I don't have time to explain this, but there is a canonical construction initially introduced by Malikov, Seisman, and Weintraub, and then generalized by Helwani and collaborators. So given a current algebroid, you can construct this vector space, and my point is this is a representation for this large n equals 4. Okay, this is the conjecture. And what is the evidence that we have about this? This theorem, and I finish with this. So we have done this case in the case that you have only one of these 0, 2 geometries, but in a way which is compatible with these large generators, these additional generators. So the theorem with my collaborators Alvarez Consul, De Arriba, and Van Ekeren from last year, hopefully we'll finish this soon, this is unpublished, is that any bismuth-Hamiltonian symmetric induces a representation of something that we call large n equals 2. So essentially, instead of having three of these n equals 2, you have only one. So it means that k is essentially 1 here. Okay, forget about the 2 and 3. So you have the same type of structure, but only one copy of the n equals 2. So we have this representation of the large n equals 2 algebra with generators as before, and this is the key. So what are these new elements that appear in the papers by Papadopoulos and Witten? They are generated by something called holomorphic divergences. So they are given by specific sections of B+, which are holomorphic in the sense that they preserve L and L bar. And if you do the calculation of what this means for a section of B+, you will see that this means nothing or less than being bismuth parallel. And I have two because I have a canonical set, vector field set associated to a bismuth-Hamiltonian symmetric, which is bismuth parallel, which is the Lie form minus the gradient of a suitable function satisfying some equations. But since bismuth also preserves the complex structure, I have the J of Z, which is also bismuth parallel. And these are the two geometric objects which generates these large symmetries. And I think I finish here. Thank you for your attention.
Thank you very much, Mario, for the very beautiful talk. So, are there any questions, comments?
I think there was one question in the chat.
Okay, thank you. I haven't seen it. Mario, do you have the access to the chat?
Yeah, Calabi Ekman, it could be an off-topic question. We know Calabi Ekman manifolds never admit balanced metrics. Does S3 cross S3 admit any kind of generalized metrics of physical consequences? Well, yeah, S3 cross S3 admits bismuth-Hamiltonian symmetrics and also admits generalized scalar where the two bismuth ridges vanish. And actually, these are bismuth flat because it comes from the construction that at least I know it from Gil Cavalcanti and Marco Valtieri, that a invariant metric on HU2 cross HU2 where you extend on the left and on the right the construction on the Lie algebra, and the 3 form is the Cartan 3 form. But there is this other result, more recent, that Bestilaf is going to speak about now, which is this nice construction. So yeah, so don't miss the next talk. She's going to talk about this. It's somewhere here. I don't know where. Yeah, examples. Yeah, this thing. So next talk. Well, my point of this talk is to tell you that these metrics are physically meaningful, even though they don't give you backgrounds like supersymmetry backgrounds in a string theory. Still, there are many things of the physical theory that you can pursue with these geometries, which are interesting, like this supersymmetry, this Lie algebra or vertex algebra representations, mirror symmetry, holography, and all that. Thanks.
Any more questions? No?
I might have a question. So, in the conjecture, what is the E? The E is the
E.
In the conjecture, what is E?
Yeah, E is the standard, is the current algebroid T plus T star with twisted by the 3 form, which is the unique 3 form, which is a torsion of the 3 complex structures on the strong HKT structure. So a strong HKT structure has a unique torsion 3 form, which is declosed. And this E is T plus T star with the Dorfman bracket twisted by this H.
Ah, okay. And I mean this, how to say, Chachman, Malikov, so they also define this chiral dome from such E tensor C.
Can you say again? What is the question?
Yeah, so you said that we need to use the chiral theorem complex, and which is defined by Chachman, Malikov, and And
how do you define that?
I mean, no, I do not remember if they define it only for tangent bundle or also for general.
Yeah, they originally in their paper they do not even talk about current algebroids. Okay, they just do some local construction where they write down explicitly generators for a sheaf of C modules over the manifold, and this sheaf is a sheaf of vertex algebras. There is a later construction by Helwani, which makes things like global in terms of current algebroids, and there is also another nice paper by Lin Shou and Matai, and they essentially show that the original construction by Marikov, Sisman, and Weintraub can be actually made global by using this current algebroid technique. So what you do essentially is you take sections of the current algebroid thought of as odd sections, odd degree, plus smooth functions thought of as even degree, and construct a suitable algebra which resembles like a Lie algebra, but it's not. It's like a Lie algebra but with further polynomial terms in the Lie bracket, and use that to do some sort of deformation quantization. And this corresponds, in the case of T plus T star without twisting, this corresponds to the Malikov-Weintraub. This is what they show. So this is more general. It's strictly more general than Malikov-Weintraub.
Okay, I see. Thank you.